Hello, my name is Shivam Kundan. I am a second-year PhD student in computer engineering at Southern Illinois University, Carbondale. My advisor is Dr. Iraklis Anagnostopoulos. In our paper, we present a methodology to improve the power efficiency of concurrently executing applications on chip multi-core processors. We utilize a combination of hardware-based application profiling and multi-layer perceptron artificial neural networks to design a runtime manager that predicts the lowest possible frequency at which an application meets its minimum performance requirement. We developed and tested our methodology on a quad-core ARM Cortex-A15 cluster embedded onto a Samsung Exynos 5422 Octa SoC. The SoC itself was part of the Odroid XU3 development board, which features a power monitoring unit. Experimental results demonstrate an average increase in power efficiency of 23% compared to a combination of Linux's completely fair scheduler and performance governor. To see why predicting the lowest possible frequency for application execution is beneficial, consider the following example. The graphs shown here depict the performance response and power consumption for three different groups of applications in response to changes in the Cortex-A15's clock frequency. Each group consists of 4 concurrently executing applications. Based on their overall shared resource utilization, we classify these groups into 3 categories. The memory-intensive group exerts high pressure on the shared bus bandwidth, greater than 1 GB per second, while the mixed group exerts intermediate pressure somewhere between 10 MB and 1 GB per second, and the compute-intensive group exerts negligible pressure, less than 10 MB per second in this case. First, let's consider the performance versus frequency graph presented on the left-hand side. Because of their differing shared resource requirements, different types of application groups reach peak performance at different clock frequencies. Typically, memory-intensive groups are bound by the speed of memory accesses, which is 933 MHz for the Cortex-A15 cluster. For this reason, the memory-intensive group reaches its maximum performance at 1 GHz, and increasing the frequency beyond this point cannot yield any further improvements in performance. Similarly, the other groups reach peak performance at 2 GHz but with diminishing returns at each increment. On the other hand, the power consumption depicted on the right increases exponentially between frequency increments, regardless of what type of workload is being executed. This is because power consumption is directly proportional to the square of the voltage, which itself is proportional to the frequency of the processor. For many groups of concurrently executing applications, this asymmetric response presents an opportunity to reduce power consumption significantly, while also maintaining the minimum required level of application performance. Which leads us to the primary purpose of our research paper, namely, how can we find the lowest possible frequency at which a group of applications will satisfy its minimum performance requirement? Our proposed methodology consists of 3 stages. First, we perform a statistical analysis of which available performance monitoring events can model the performance of a given workload in the most accurate and stable possible manner. In this stage, we decrease the number of inputs to our subsequent neural networks from 66 to 4. Next, we utilize the shortlisted performance events to construct a training set for a group of multi-layer perceptron artificial neural networks. By performing a supervised learning, we train the networks to output the lowest possible frequency required to maintain minimum application performance. Finally, we utilize the trained neural networks at runtime in order to dynamically adjust the operating frequency of the processor whenever a drop in performance is detected. The aim of reducing the number of inputs is twofold. First, in terms of execution overhead, it is cost prohibitive to switch the counted event types at runtime. Since there are only 6 performance monitoring counters available, we must decide which 6 or fewer events can best quantify the execution characteristics of the workload being executed. Second, Reducing the number of inputs to our neural network reduces computational complexity and consequently the runtime overhead. We accomplish the reduction in number of events by using statistical techniques to reduce multicollinearity among the recorded event counts. We begin by executing groups of concurrent applications representing a wide range of shared resource utilization while recording the counts of all 66 available events. We repeat this procedure for each available frequency of the processor. Next, we calculate the standard deviation for each recorded event while executing the same application mix. The goal is to identify events whose value does not deviate significantly when executing the same group of applications. The table shows the top 18 results in descending order of deviation. Note that the events are related to the various components of the memory hierarchy. They model the data well because shared resource utilization is one of the primary determinants of application performance for chip multi-core processors. The events that show the most deviation for the same workloads relate to speculative execution, such as the event dpspec, which measures the number of instructions speculatively executed for integer data processing. For each pair of events, we calculate Pearsons product moment correlation, which is a measure of the strength and direction of association that exists between two variables. This produces an absolute value between 0 and 1 for each pair of recorded events, indicating the extent of correlation between them. A value of 1 indicates complete correlation, while a value of 0 indicates no correlation. The ideal combination is one where correlation among all events is closest to 0. Therefore, selecting a combination such as bus accesses store and L2D cache writebacks would deprive our neural network of valuable information. In contrast, L1I cache accesses and L2D cache writebacks are a good combination of events since they record nearly mutually exclusive information. Previous research has shown that the quad-core Cortex-A15 cluster can be modeled effectively by using 4 events. Therefore, we select the top 4 events with minimal correlation to each other. In this stage, we use the selected performance events to construct a training set for a group of MLP neural networks. Our methodology uses one neural network per performance threshold. Each neural network takes the summed values of the selected events as input. The input x sub f describes the current state of execution for any given group of applications. The neural network then selects the target frequency that satisfies the performance requirement from one of 10 available classes, with each corresponding to an available frequency of the processor. To construct the training set, we sum the per-core values of each selected event. For each group of applications in the training set, we identify the minimum frequency at which the required performance is achieved. Next, we combine the target frequency of each group with its input vector and perform supervised learning using the Orange data mining application. We save the final weights for use in the next stage. The trained neural networks are converted to lookup tables for use at runtime. Application execution is divided into discrete time quanta. At the end of each time quantum, the runtime manager checks if the group's performance threshold was satisfied. If there is a drop in performance, it triggers the appropriate neural network and scales the processor to the required frequency. On average, the time taken for predicting a new frequency is 20 microseconds. We use the metric speedup factor as a baseline to evaluate the performance of each group of applications. This metric indicates a performance ratio which is normalized to the maximum possible instructions per second of the specific workload. For example, if a group achieves a speedup factor of 0.97, it implies that it was able to execute at 97% of its maximum possible performance as measured by instructions per second. We evaluate our experimental results for 9 different groups of applications. This set represents a broad spectrum of shared resource utilization for the Cortex-A15 cluster. We then compare our results with those obtained from using Linux's completely fair scheduler and 4 default power governors: performance, interactive, conservative, and on-demand. We exclude the power save governor because it sets the frequency to the minimum possible level, which is impractical in terms of application performance. The graph depicted here shows each of the 9 application groups in decreasing order of shared memory bandwidth. Applications that require higher bandwidth suffer from performance saturation after a certain frequency. Using our approach, we were able to identify this maximum frequency while also meeting the 3 minimum speedup factors for each evaluated application group. Consequently, our proposed approach achieved lower power consumption for 8 out of 9 application mixes while maintaining the same level of performance as the other methods. We successfully reduced the power consumption by an average of 19% compared to Linux and 5% compared to the memory reads per instruction method. Memory-intensive application groups benefit the most from our approach due to their logarithmic relation between IPS and frequency. Specifically, for the memory-intensive mixes number 1 and number 2, the proposed approach selected an operating frequency that reduced power consumption by 14.6% and 16.5% respectively compared to Linux's CFS and performance governor. On the other hand, for purely compute-intensive groups such as for mixes number 8 and number 9, our method displays the same behavior as Linux's performance governor. This happens because the constituent applications of these groups do not suffer from resource contention, which results in high individual performance even when executing in a group. In terms of power efficiency, measured in million IPS per watt, our proposed approach outperforms Linux's performance governor in all evaluated scenarios. For the highly memory-intensive mixes number 1 and number 2, we are able to increase MIPS per watt by 20% and 22% respectively. In the case of the most compute-intensive mixes, number 8 and number 9, we increased MIPS per watt by 24% and 19% respectively. On average, we improved power efficiency by 23% compared to Linux. The MRPI approach achieves better power efficiency for mixes number 1 and number 2 because it sets the frequency of the processor in relation to the most compute-intensive application in the mix. Since these mixes did not contain any compute-intensive applications, the MRPI method was able to select an extremely low frequency, resulting in high power efficiency. However, our method is able to outperform the MRPI approach for all other mixes, yielding an average increase of 13% in power efficiency. As a result of high performance and low power consumption, we decreased the total energy consumption of the evaluated mixes by an average of 21% over the performance governor and 18% over the MRPI approach. In our paper, we present a methodology to improve the power efficiency of concurrently executing applications on chip multi-core processors. Essentially, the methodology answers the following question. Given a minimum performance threshold for a group of concurrently executing applications, what is the minimum possible frequency that will satisfy this threshold? Experimental results on a quad-core ARM Cortex-A15 cluster demonstrate an average decrease in power consumption of 19% and an increase in the power efficiency by 23% compared to a combination of Linux's completely fair scheduler and performance governor. In addition, we are able to decrease the total energy required to execute each application mix by an average of 21%. Thank you.